Hello, everyone. I'm Hengkai from Penn State. And today, I'm going to share our work, VIPER supporting Syscall-Guard variables for data-only attacks. Control flow hijacking is a predominant approach to exploit memory bugs in past decades. So in control flow hijacking, attackers first need to manipulate memory bugs to gain memory-accessed primitives like arbitrary read or write, and then use these primitives to corrupt control data like return address or function pointer, which further divert the control flow to achieve malicious goals. To prevent such attack, researchers have developed many defense solutions. For example, code pointer integrity can secure control data, and the control flow integrity can prevent abnormal control flow being executed. Nowadays, it is difficult to hijack control flow. At the meantime, data-only attacks are still possible and powerful. Unlike control flow hijacking, data-only attack only corrupts non-control data but achieves similar malicious goals. Since non-control data plays such an important role in data-only attack, the question is how to automatically identify security-critical non-control data, or we call it critical data. Supporting critical data is important but also challenging. Unlike control data has common low-level properties, for example, specific data type or memory location, critical data are defined based on high-level semantics. However, general analysis to infer high-level semantics is impractical, especially on large programs. In previous work, researchers tried to manually inspect code to identify critical data, which require large human efforts and not scalable. Flow stitch can only identify critical data with explicit source or well-defined things, like Syscall arguments. And Clarity can only identify critical data related to error codes in Linux kernel. In this paper, we first identify an important category of critical data called Syscall-Guard variables. We designed branch force to identify them and assess their capability. We implemented a framework called VIPER to realize our idea. We identified 34 previous unknown Syscall-Guard variables and built 4 new data-only attacks. We open source our tool. Let's start from a classic data-only attack. The code is for OpenSSH server to authenticate users. Authenticated is an integer. A while loop retrieves usernames and passwords from network and verifies them. If correct, the server will set authenticated to 1 and break the loop to log in. However, attackers can leverage a bug in packet read to set authenticated to 1 and log in the server even with wrong password. So here, we call the authenticated is the critical data. And the question is how to identify variables like authenticated. To answer this question, we first conducted a comprehensive study on existing data-only attacks and get 2 observations. First, most data-only attacks rely on security-related syscalls, like execute in this example. Second, security-related syscalls are often guarded by security checks in the form of conditional branch, like the if statement. We consider this kind of branch is Syscall-Guard branch, and the variables in this branch are Syscall-Guard variables. And we implement VIPER to automatically identify them. Before going deeper, we want to know whether Syscall-Guard variables really matter in data-only attacks. By checking existed 17 data-only attacks, we found 11 variables are Syscall arguments, which can be identified by previous work like flow stitch, and all others are Syscall-Guard variables. However, it is challenging to identify Syscall-Guard variables. The first challenge is how to identify the sole contribution of each variable to trigger a syscall. Symbolic execution can identify a complete path to a syscall, but it cannot tell which variables are more critical. The second challenge is how to make the analysis efficient and scalable. Static analysis could be used, but it has limitations on handling indirect calls and conducting interprocedural analysis. To efficiently locate the sole contribution of each branch, we design branch force. The core idea of branch force is to flip every branch during execution and hook syscalls to see whether there are new security-related syscalls get triggered. If yes, we consider the flipped branch is a Syscall-Guard branch. For illustration, given a program and the input, we will first run the program with the input and record all visited branches and trigger the syscalls. And then we will rerun the program with the same input, but forcefully flip the first branch on the path. If there are new security-related syscalls get triggered, we consider the branch is the Syscall-Guard branch. We flip every branch on the path and record all Syscall-Guard branch. Through branch force, we can obtain a bunch of potential Syscall-Guard variables, but not all variables can be corrupted via memory bugs. Therefore, we need to assess their capability. The general idea is performing backward data flow analysis for each Syscall-Guard variables. We design two metrics to assess their capability. The first metric is memory location. We consider global variables are easier to be corrupted compared with the heap and the stack variables. The second metric is the number of memory write instructions. We assume every memory write instruction could be abused by attackers with the same probability. Therefore, more memory write instruction within the lifespan of the variable indicates higher probability of being corrupted. And more details can be found in the paper. Here is the workflow of VIPER. Given a program and input, branch forcer will first dry run the program to collect all triggered syscalls and visited branches, and then flip every branch to identify potential Syscall-Guard variables. We only flip unique branch and use fork server to speed up the re-execution. Variable writer will then first re-execute the program and record execution trace on LLVM level, and then simulate the execution based on recorded trace and perform backward data flow analysis. VIPER will report all Syscall-Guard variables with a high probability. We evaluate VIPER on 20 programs, 9 with known data-only attacks, 7 from FuzzBench, and 4 other well-tested programs. We take 3 ways to collect corpus. We will first search corpus in the source code repository or online. If cannot find, we will fuzz the program with AFL++. We totally identified 36 Syscall-Guard variables from 14 programs. And this chart shows the Syscall distribution. We can see 15 variables are related to unlink or rename, which can delete or overwrite files. And 10 variables are related to execute, which can execute arbitrary code. We also investigated the exploitability. We first emulate the memory write primitive in GDB to confirm that security-related syscall can be triggered. Then we investigated historical vulnerabilities. For 16 variables, we confirmed that there is a CVE exists in their lifespan and can provide memory write primitive. And finally, we built 4 new data-only attacks on 2 programs. We evaluate the time costs of VIPER. In most programs, VIPER can finish analysis within 5 minutes. We also compare VIPER with FlowStitch, which is an exploit generation tool for data-only attacks. We can see the time cost is at the same level. So we can combine VIPER with FlowStitch to generate data-only attacks automatically. Here is an end-to-end attack on V8. V8 is a JavaScript engine widely used and contains more than 3 million lines of code. VIPER confirms one highly probable variable in V8, which is a global variable with a large number of memory write instructions in its lifespan. The variable is called enable OS system, and only when the value is not 0, V8 can call the library function system. We use an old CVE to bypass ASAR and set the enable OS system to 1, so the attackers can call system to execute the arbitrary command. And here is the attack demo. We first run a script to show the normal behavior. We can see with the default setting, V8 cannot call system to run a bash. And it is only allowed by setting option enable OS system. And we will perform our attack with 40 ASAR open. And here is the POC of our attack. We will first use the CVE to bypass ASLR and modify the enable OS system to 1, and then try to call system to run the bash again. And we can see in our attack, we didn't need to set any option, but with the default setting, and we can run the bash. In summary, we implemented VIPER to automatically spot Syscall-Guard variables for data-only attacks. We designed branch force and assess their probability. We fed 34 previous unknown Syscall-Guard variables and built 4 new data-only attacks on sqlite and V8. We open source our tool and the exploits. Thank you. I'm ready for questions.
Thank you.